Welcome everyone to Data Science DC. Again, my apologies for getting started a little late, but appreciate you all sticking in with us here. My name's Tommy Jones. I'm one of the co-hosts here, and I've got some introductory slides. But our main event is Yasol Jian, who's going to be talking about network-based trajectory analysis of topic interactions for COVID-19 literature. And slides were going in the wrong direction, sorry. So for those that maybe are just joining us for the first time, Data Science DC is part of Data Community DC. We're an umbrella organization for several data science-based meetups in the Washington, DC area. We're a nonprofit that is dedicated to building a community of practice around data science in the Washington, DC area, although since for the last couple of years, due to COVID-19, we've been remote. And so we've been able to get both speakers and participants from all over the world. I believe, Yasol, you're joining us from Korea, is that correct? Yeah, so would not be possible if it wasn't for the miracles of modern communication technology. You can see our website here, and you can follow us on Twitter at Data Community DC. Big thank you to our sponsors. The Zoom license that allows these events to go on is not free, and hopefully we'll be going back in person, and there's some expenses that go along with that as well. So Prefect and ATA help us afford to hold these events. So these are the co-organizers for Data Science DC. I'm Tommy Jones, and you can also see on video Janet Dobbins. She and I are two of the co-hosts. We also have Jeff Hale and Christopher Smith, who I don't believe are here with us today. But these are our email addresses and Twitter handles if you all want to email us, Janet at datacommunitydc.org, Jeff, Thomas, and Chris. We'd love to hear from you. We do have a code of conduct here. I have a policy against reading slides for people, but the basic gist of it is we would like everyone here to treat everyone else with dignity and respect. We have a zero tolerance policy for harassment. If you experience any harassment, which I guess with Zoom that might be taking place over chat, I'd ask you to send a message to me or to Janet. I'm here as Data Community DC, and Janet is here as Janet Dobbins, and we will promptly take care of the situation. We also have a diversity statement. So in the before times when we all met in person, this would be where I would ask everyone to look around the room and see the diversity of races and genders that come to attend these meetups. And our commitment to the community here is to have our speakers reflect the diversity of the audience. And so what we ask is that our audience hold us to that. If you feel we're not doing a good enough job at bringing diverse speakers and perspectives to you, please don't hesitate to reach out to Janet, myself, Jeff, or Chris, and let us know. And that's a situation we take seriously, and we want to make sure that our speakers represent the audience. So we've got a couple events coming up for Data Science DC. On May 10th, we're going to have a talk on scaling and distributing Python and machine learning applications with Ray. And then on June 14th, I will actually be speaking, and it will be on fine-tuning for latent Dirichlet allocation for transfer learning. And you can, I assume if you're in the audience here, you've already found us on meetup.com, but there is our web address. We also have a YouTube channel, so we're recording this. And so you can go to youtube.com/datacommunitydc and join us there. We also have a Slack channel. and we'd love to see you there and participate and be able to build community discussions there in between events. I'll post both of these links in the chat, and feel free to check them out and join. Now we're going to turn to community announcements. Since we're doing Zoom, we don't have it so people can come off their microphone. But what I'd say is, if you're holding an upcoming event, I know Will Angel's in the audience here. He's one of the co-organizers for DataViz DC. So if you're holding an upcoming event or a meetup or something like that, please post it in the chat so that others can know about it. Sorry to pick on you, Will. If you're looking to hire, if you're looking to be hired, or if you have any other event that you'd like the community to know about, this Thursday, Will says, is Data Visualization DC. But please post it in the chat there. I also neglected to mention earlier, but this event is in conjunction with the text analysis interest group in the American Statistical Association. So last summer, Yasol and I won presentation awards for our research at the Joint Statistical Meetings, which is a large multinational gathering of statisticians. It's a real party when you get that many statisticians in a building together or online together. But we, Yasol won one of our awards, and in conjunction with the text analysis interest group, we're presenting the research here at Data Community DC. And so with that, I'm going to get off the stage because you didn't come to see me, you came to see Yasol. So I will stop sharing my screen and turn it over to you, Yasol. Thank you.
Thank you. Okay, here we go. So can you see my screen? Is everything good? Okay, thank you.
Yep, we can see it.
Yep. So, hi, my name is Yesel John, and I'm a PhD candidate at Yonsei University in South Korea. And first of all, I would like to thank for giving me an opportunity for present my research at Data Science DC. So today I'm going to talk about network-based trajectory topic interaction map for text mining of COVID-19 biomedical literature. So I will begin with how we found our interest in this subject with several research questions. And then I will introduce methodology that we have based on to handle the issues that we came up with. And finally, I want to share the result of our result of applying our approach to COVID-19 biomedical literature and end up with summarization of this work. So, yep. Since the emergence of the worldwide pandemic of COVID-19, there are relevant research has been published at dazzling pace, which makes it hard to follow the research in this area without dedicated effort. And it led to the rich amount of biomedical literature about COVID-19. So as of June 2021, searching with the thumb COVID-19 and the PubMed biomedical literature database resulted in more than 140,000 publications. However, given the rich volume of COVID-19 literature and its rapid publication phase, it is practically impossible for biomedical experts to trace all of this literature manually in real time. So using the property of the text data, it is of great interest to cluster words effectively and understand the meaning of these clusters. So in the text mining area, topic modeling is the most well-known approach for this purpose. And there have been many attempts to analyze literature text data with several topic models, especially latent Dirichlet allocation model has been applied to biological literature and showed that it can be a practical solution for bioinformatics research. However, it is important to note that it is hard to find the data that contain independent topics towards one subject in the real world. Still, instead, multiple topics are often intercorrelated. Therefore, to tackle this practical issue, there have been attempts to model interactions among topics by modeling the correlated structure within the topic model or combining the topic model with statistical models. So one of statistical methods for handling correlated structure is network analysis. Specifically, network modeling estimates the relationships of interactions among nodes based on their dependency structure. It provides global and local representation of nodes at the same time. Therefore, our study aims to estimate the topic's relationship and visualize their dependency structure simultaneously by considering the interaction among topics using the network model. So this figure illustrates the proposed approach for trajectory topic interaction map. So here, first, here, as a step one, we process text mining results with natural language processing and construction of the word corpus. And then as a step two, we extract topics, each of which is defined by its own topic word distribution, which is estimated from the topic model. And as a step three, we estimate the interactions among topics based on their topic words distribution using the network model. And finally, as a step four, we visualize the interaction relationships among topics using the trajectory plot showing the transition of topics coordinates. So I will briefly introduce the details of each step from the following pages. So there are many other topic models, but we chose Biterm Topic Model to extract the topics from COVID-19 literature. So this is because since COVID-19 is a hot topic and its research is active and ongoing, some articles are released without full context, but only abstract. So abstracts of the COVID-19 literature can be categorized as short text. Therefore, we implement Biterm Topic Model called BTM, which can efficiently handle the short text data. So BTM makes up for the lack of words in the short text data by replacing words into a Biterm, which is the pair of the words. So it assumes that two words are belonging to some hidden clustered set of words. Therefore, we need two sets of parameters to estimate the topic distribution, theta, and the topic words distribution, phi. It sets each topic with the latent variable z, and word follows the multi-nomial distribution with parameter theta and phi respectively. And the prior distribution for phi and theta is set to Dirichlet distribution with hyperparameters beta and alpha respectively. So therefore, we could construct the likelihood like this. And based on that, we could estimate the posterior distribution of conditional probability of latent variable z using the collapsed Gibbs sampling. So after some iterations, we can construct the distribution of words distribution and topic distribution. So by using words distribution and topic distribution, we could construct the topic words distribution, which is our main interest over here, the phi w given z. So our idea was we regard the topic words distribution as a topic words matrix XQ. So each cell is composed of probability for the degree of association of each word with each topic. Since the output of each topic words distribution includes all words, we might not be able to determine the characteristics of topics if we use all the words at the words that topics share. For example, these could be some common words such as people or human or world or and so on like that. So we need to select only the meaningful words from each topic to estimate the relationships among topics based on their words. So to select the meaningful words, we calculate the coefficient variation and maximum probability from each row of matrix XQ. So in short, we consider the unique characteristic of each topic and reasonable high probability in at least one topic. So there are two reasons for choosing a coefficient variation and maximum probability as a criterion to select words. First, it is expected that important words have large variation in probabilities among topics so that it represents the characteristic of topic distinctively. And second, in order to be a meaningful word, it should also have high probability in at least one topic. Therefore, by differing the proportion of words, we can set different sets of XQ, matrix XQ, XQ. So in short, the number of row of matrix XQ is the same. Like for example, the N, it might be the number of the topics. And on the other hand, the number of columns of matrix XQ, which is P over here, is different because we set the different portion of the words from based on their coefficient variation and their maximum probability. So the number of P is different depending on the matrix XQ. So the word set is different. So based on these several different sets of matrix XQ, we implement the network model. So as a result, we could model the topic word matrix XQ, which can be regarded as a bipartite network. So with this matrix XQ, we estimate the interactions among topics based on the different word sets and visualize their relationships by mapping on the interaction map, which is estimated by the network model. So overall, first, we estimate the latent positions of topics based on the network model. So here, the table could be the matrix XQ. So it has a different portion of word sets over here. And we apply this each set with the network model so that we could estimate the latent positions of topics. And then second, we map on the R2 space like this, using the estimated latent positions of topics. So to estimate the interactions among topics, we adopt the concept of latent space item response model called LSIRM. So it views item responses as bipartite network and estimated the interaction between respondents and items using the latent space. Here we can regard the topic as items and words as respondents. However, the original LSIRM cannot be directly applicable because our input data matrix XQ has continuous probabilities indicating how likely each word belongs to each topic. Therefore, in order to apply LSIRM to our input data XQ, we need to expand the original model to a Gaussian version. So this is the modified Gaussian LSIRM, which is described in details as follows. Here, each matrix XQ indicates matrix small xij, which indicates the probability of word J belong to topic I based on topic words distribution, which is from XQ. And here the total number of J is different depending on the matrix XQ. And however, the number of topic I is same, yeah. And here the UJ implies the latent positions of word J, and VI implies the latent positions of topic I. So the latent positions of topics are estimated by Euclidean distance between the latent positions of word J and topic I. Therefore, the latent positions of topics can be estimated based on the distances with words. For example, if the two topics share the same amount of words and same characteristics of words, then they are more likely to be positioned near to each other. So, and for about the prior distribution, I'll see details in our paper preprint in archive. And this is the posterior distribution of Gaussian LSIRM. So we use Markov chain Monte Carlo to estimate the parameters of Gaussian LSIRM. For several different set of matrix XQ, we could estimate each latent positions of topics I, where each XQ has the same number of topic I, but has different number of words. So using these latent positions of topics, we can trace the coordinates of each topic using these latent positions to comprehend the topics relationships from various viewpoints. However, the network modeling contains invariant problem. We implement cross matching within the MCMC samples and between the matrix XQ with baseline matrix X baseline. So we use cross matching inside the MCMC samples because after updating the latent positions of topics from each MCMC samples, we need to align the samples to get the final estimates of the latent positions of the topics. And on the other hand, to trace the coordinates of latent positions from each matrix XQ, we need to process cross matching between matrix XQ. So simply this cross matching is rotate other matrix XQ based on the baseline matrix. So here we set baseline matrix for rotating MCMC samples as some matrix which shows the maximum likelihood. And on the other hand, we define the baseline matrix for among the matrix XQ as the matrix which shows the most dependency structure among the topics. So you may ask how to define the dependency structure among topics. So as you see, page 13 here, if the topics don't have any dependency structure among other topics, then the distances between the topics and words are all the same. I mean, the latent positions are located at 0 point. So the dependency structure refers to how far the latent positions of topics are located from the origin. So, so we choose the matrix X baseline, which shows the most dependency structure among topics. That means that topics are the latent positions of that topics are located far from the origin. We also invent the scores for validation of our result which measures the words relations to topics. As I shared before, here J indicates word and I indicates the topics. So therefore, the Sij is the score which quantified the closeness between word J and topic I. It composed of two parts. First, the delta Ij indicates the probability of word J belonging to topic I given by topic words distribution. And on the other hand here, the gamma Ij indicates the distance between the latent positions of word J and topic I, which is estimated by Gaussian LSIRM. So here, the W1, W2, W3, and W4 are the weight for exclusivity, and here the ECDF is the empirical CDF function. So for example, in the first term of the Sij here, it measures how the delta Ij is ranked among the other topics when the word J is fixed. And here, the second term of the Sij here is that the delta Ij is ranked among the other words when the topic I is fixed. So these words like here, the gamma Ij and the last term as well. So this is the score we invented. So yeah, finally, from now on, I'm going to share our application results. And we applied our workflow to the COVID-19 literature, which is published between December 1st, 2019 and August 3rd, 2020 from the PubMed. So we collected articles of which titles contain coronavirus 2, COVID-19, or SARS-CoV-2. And this resulted in total approximately 35,000 articles. And after pre-processing the text data, we obtained about 15,000 documents and about 9,000 keywords. So we set the number of topic as 20 to implement BTM. For the hyperparameters, we assigned alpha as 3 and beta as 0.01. Since our main goal is to visualize the topic relationships, we empirically searched and determined the hyperparameters. So after implementing BTM, we can obtain the topic words distribution. So this is the topic words distribution. And this table shows the structure of topic words matrix, which is from the topic words distribution. And within the topic, each cell indicates the probability of degree of relativeness or word to a specific topic. And this figure shows the histogram of log transformed word probability for each topic. And as we can see, there are two clusters of words that are relevant to each topic, and other here, the left side, is redundant words such as like human, people, or some common words. Therefore, we select here the meaningful words based on the two criterions which I shared before, the coefficient variance and the maximum probability. So it makes sense that representative words of topics have large variation in probabilities among topics. Moreover, in order to be a meaningful word, it should also have high probability in at least one topic. So specifically, we obtained the multiple matrix XQ corresponding to top 60% to 40% of words determined based on the two criterion, the coefficient variation and maximum probability. So therefore, the Q can be 40 or 41 to 60. And the number of words corresponding to the 60th and 40 percentiles were about 2,600 and 1,000 respectively. So LSIRM takes each matrix XQ as input, and we implement the pro-cross matching within the model. Since we estimate the latent positions of topics on the two-dimensional Euclidean space, we could obtain each latent positions of topics with dimension of 20 times 2. So the 20 means the number of topics. And here 2 is the 2 dimension of coordinate, which is estimated from the network model. So to trace the latent positions from each matrix XQ, we need to define the baseline matrix which has the most dependency structure among topics. As I shared before, the topic close to the origin is more likely to have weaker dependency with other topics. So here, the left figure is the plot of the average distance of latent positions with origins within each matrix XQ. So this point indicates the average distance of the latent positions from the origin from the matrix X40, right? And as we can see, the latent positions of topics from the matrix X47, which is here, contains the 47th percentiles of words, start to show the high dependency structure among topics. So there are two possibilities that can lead to low dependency over here. Because first, it is possible that there were a small amount of words that could distinguish the characteristics of their topics from the other topics. And second, it is possible that the most of the words were common to share with other topics. So here, the right plot is the estimated latent positions of topics of matrix X47. So therefore, we implement pro-cross matching among matrix XQ based on here, this matrix X47. So we rotate each of the latent positions from each matrix XQ based on the latent positions of topics from the matrix X47. All right, so we calculated the score Sij for each word J with topic I based on each matrix XQ. And yeah, this figure shows the two different scenarios of the plot of score and affinity. So here the affinity is, we define this as distance gamma in exponential so that we can compare more directly between the score and affinity. So here, if the affinity value is high, then it means it refers to have a close distance between word I and topic, word J and topic I. So here, the orange colored refers to top 20 words with high value in score. So according to the figure, we found two scenarios. And the first scenario is that the latent positions of a particular topic is located at origin, such as here, topic 19, topic 14, or 20, or 2, 7, or 13. Is the this plot is topic 19 in matrix X47. And from the left figure, the plot of score and affinity in this case shows two clusters, one with the high score and high affinity, and the other with a low score but high affinity. Because this topic has many words in common with other nearby topics, although there are some words close to that topic, they were not close enough to distinguish the characteristics of that topic based on the probability of words belonging to it. So on the other hand, this is the plot of topic 3 in matrix X47. And the right figure is the second scenario, is that the latent positions of some topics are located far from the center, like 3 or 6 or 4 and 10 and so on. So this indicates that they have distinctive characteristics compared to other topics. So there is only one pattern in this case. It has the high score and high affinity because those words are both close to those topics and have a high probability within those topics. So with the score, we could list up the top words from each topic. Then we named that each topic based on each selected top scored words. So this is the table of the topic names based on the top 20 words from matrix X47. And here is the score we calculated from the previous slide. So it means that subplural is the word that is high, most related words to the topic 1, which is we named it as a long scan. So for further details, please see the paper preprint, which is available in archive. So this is the result of the topic names. So finally, this is the trace of the interaction map. And we interrogated what kind of the topics have been extensively studied in the biomedical literature on COVID-19. In addition, we also studied how those topics were related to each other based on their closeness and the sense of latent positions. So this is the latent positions of topic 2. And this arrow indicates how the topic 2 is changed based on different set of matrix XQ, which contains the different number of words. So we also partially clustered the topics based on their relationships using the quadrants. So this allows us to check which studies are about COVID-19 are relevant to each other and could be integrated. So we found that this trajectory interaction map delivers 3 topic clusters, A, B, C. So about the A, it is about COVID-19 and its effects on the different areas. And the cluster B indicates the symptoms and treatment of the COVID-19 and its relative studies. And here, the cluster C indicates the molecular studies associated with the COVID-19 infection. So moreover, it displays the trajectory plot, and it shows how topics are positioned on the latent space and how these topics make transition. So more specifically, the direction of arrows, which I mentioned before, refers to how topics coordinates changed as the number of words decreases. So for detailed explanation, please check our paper print, which is archived in now. And so, yeah. So to summarize our research, we estimate and visualize the topic relationships by mapping unobserved interactions onto the interaction map using the network model. And we visualize the topic interaction map as a trajectory plot to detect the change of interactions of topics over different sets of words. Moreover, this approach helps organize a tremendous amount of literature and mind underlying the relationships among topics based on the literature. So yeah, we spell out all these details in our paper preprint, and currently we are working on future direction to extend this analysis to more general cases. And to validate our model, we are working on the supervised learning approach, such as label text data set. So yeah, if you have any question, so I'm happy to answer that, and feel free to ask me. And yeah, thank you for your undivided attention. Thank you.
Thank you, Yasol. That was great. So for folks on the line, if you have any questions, please drop them in the chat. In the meantime, I have a couple questions for you, Yasol.
Okay.
So what software did you use to do your analysis?
Oh, come again. So
Which software, like which
yeah,
programming languages and packages?
yeah, thank you. I kind of like for topic model, I use the Python, and to estimate the top latent positions of topics, I use R software. So I kind of
Okay.
like mix them.
Cool. And what was the most challenging aspect of the research for you for the whole project?
All right. For me, the reason why we use the several different set of matrix XQ is because we don't have any expert knowledge to cut the um, to select the meaningful words from the word set. So that was the most challenging thing, to select how to select the meaningful words from the whole word set. So that's why we came up with the, how about just select the several word sets and compare them and trace their plot to see the overall structure of the topics. So yeah, that was the most challenging thing for me, to select the meaningful words without having a knowledge, expert knowledge. Yeah.
Yeah, that's one of the most challenging things for most people, I think.
Right.
And so what are the next steps for your research? You said you were going to try it for more general corpora. Do you have longer term plans here?
Oh, yeah. Thank you for asking me. And um, uh, actually, we applied this approach to different areas of text data. For example, the government text data set or other data set, and it works really well. And but we are more focused on the validation. So as I mentioned before, the text data set with the label text data is not common. So it is hard to validate the result of text modeling. So we are looking for some label text data set to validate our model. Or moreover, we are currently working on the topic clustering. I mean, these kind of like lines are drawn by myself. So by interpreting the result of the topics. However, we are looking for some cluster methods that capture the real cluster set of the topics. So yeah, we're kind of working on that.
Okay. And how close are you to finishing your PhD?
Oh, I still have to wait 2 years, I guess.
Lots of work ahead of you then.
Yes.
Well, I don't see any questions in the chat, so I'm gonna say last call. Does anyone have any questions? Feel free to put them in the chat. I don't see any coming in, so I will, I guess I'll leave it there. Yusol, thank you so much for presenting for us today. Your research is very interesting. I got some ideas from it, and I want to go try it out a little bit. So,
Great. Okay, thank you for inviting me. Yeah, it's a really great opportunity for me. Yeah.
all right, thanks again. Bye,
Bye.
everyone.
Thank you.